Hello, everyone. In this presentation, I'm going to talk about a variation of entropy accumulation theorem called marginal-constrained entropy accumulation theorem, which we termed it as MEAT. It is suitable for analyzing prepare and measure QKD protocols, and it's a joint work in collaboration with Ernest Tan. So let's start with some preliminaries. We begin with the notion of source replacement scheme, which essentially tells us that for the security proof purposes, we can, instead of analyzing a prepare and measure protocol, we can convert it into an equivalent entanglement-based protocol, where instead of having Alice picking some states from an ensemble and sending it to Bob, she instead prepares an entangled state, send part of it to Bob and keep the other part to herself, and afterwards performing some suitable measurement on her side of the states, such that the resulting state would be as if she has picked these states from the ensemble in an actual prepare and measure case. However, there's a small but extremely important nuance here, and that is that because the margin of Alice never left the lab, it has to be we have to sort of incorporate that this marginal has to be fixed because the adversary could not ever touch it. And so any framework that we develop such that we wish to be compatible with this source replacement scheme has to be somehow incorporating this fixed marginal problem. Okay, moving on to the leftover hashing lemma. So leftover hashing lemma essentially tells us that connects the length of the extractable secure key rate to some form of conditional entropic quantity. So a traditional LHL connect this to the Smoothman entropy of the raw key register condition on Eve side information. Whereas recently there's been a new Rennie version of leftover hashing lemma that is written based on the sandwich Rennie entropy, which turns out to be of the simpler form and leads to tighter key rates. This new sandwich Rennie entropy is parameterized by real parameter alpha, but to get us a little bit of an intuition of what this thing is, we can look at the regime where alpha is bigger than 1. In that regime, if we look at the extreme cases, they are corresponding to the usual von Neumann entropy and the min entropy. So we can see that these Rennie entropies are sort of interpolating between these two extreme cases. Okay, now moving on to the zoo of entropy accumulation theorems. So we'll begin with the original EAT, which was suitable for the entanglement-based protocols for the device-dependent cases. Later on, it was generalized to the JIT framework, which was designed for analyzing prepare and measure protocols. However, there were two main drawbacks with the JIT framework. The first one was that the bounds obtained within that framework were suboptimal. And the second one was that it suffers from a restriction that we termed as repetition rate restriction, and which limits the applicability of the protocol in the framework in practical scenarios. So the first limitation was already resolved in our previous work, and the second one has been addressed in the sequence of works, including this one, which I'm going to term them under the umbrella term of the MEAT type statement, where essentially the idea of all of these developments was to instead analyze the source replaced equivalent protocol. Okay, now let's go to the main part. So I'm going to explain briefly to you the simplified version of the MEAT. So we begin with the source replaced version of the protocol, where Eve holds onto a global entangled state, and she sends the A registers to Alice and B registers to Bob. And we note that the marginal analysis state has to be fixed. And each round of the protocol is being explained by each of these M channels by measuring Alice and Bob's registers and their output 3 different registers. A test data, C registers which is going to be used for acceptance tests, a public announcement register, and a raw key register. And the goal here is to bound the global conditional entropy condition on the protocol being accepted. So the basic version of this framework was already resolved by Van Himbeck and Brown, where they assumed that all these M channels are basically the same. Later on, it was slightly generalized by Fauzi Kochanovsky concurrently with this work to the case where channels are still in tensor product, but they can be different in each round. And in this work, we even generalized it further to handle even broader class of protocols for the case where channels are not necessarily in tensor product. But what is the form of the bound that we would get using these MEAT type statements? So for that, let us look at the most basic case where all the channels are basically the same, in which case the bound we would obtain has the following form. where the single rank quantity is given by this H up arrow alpha, which contains an optimization that preserves the fixed marginal analysis register, allowing us to analyze the source replace protocol. And the correction term is given by this log probability of accept. And the accept event is defined via having this frequency distributions over these test data registers lies within some predetermined acceptance set. Okay, but what is this single rank quantity exactly? So for that, it turns out, let's look in more detail. It turns out that the single rank quantity is given by the following optimizations, where the inner optimization is over all the output states of the M channel with fixed marginals, and the outer optimization is over the acceptance set, which is essentially a set of probability distributions that are delta close to the honest distribution. And for the objective function, the first term is just a linear combination of conditional entropies. And the second one is basically a classical relative entropy between the distributions in acceptance set and the distributions that are actually being generated by these M channels. But to get a little bit of an intuition of what this thing is, let us look at the asymptotic limit, which corresponds to the limit of alpha to 1, which basically we can recover the following results, which is you can see that we are ended up with an optimization with a hard constraint where the probability distributions has to lie within the acceptance set. Now, if you compare this to the finite size case that we had, this hard constraint optimization is somewhat transformed into a soft constraint by having this penalty term, this classical relative entropy term, acting as a penalty for violating the constraint where the distribution goes outside of the acceptance set. And so we can see that this single rank quantity in the finite size regime is smaller than the asymptotic one, but converges to that one as alpha goes to 1. All right. Now let's look at the most general form of the meat, which has the following sequential structures, where the A registers correspond to Alice's register, which are going to be kept in her lab. The E registers are adversary side information, including the public announcements in each round. And the E0 register, where we start with, could contain all Alice's signals at the beginning. And S and C registers are basically the same as before. So it turns out that even for the most general form, the form of the bound we would obtain along with the single rank quantity are quite similar to the simplified case. But why do we care about this more general form? What advantage does it have? Well, first of all, it allows for analyzing on-the-fly announcement, which means that Alice and Bob could actually make their announcements before the quantum phase of the protocol is actually being done, which is useful in practical scenarios. And second of all, even though we have these sequential structures, I'd like to point out that there is no repetition rate restrictions whatsoever in the meat framework as opposed to the previous ETH results. And so the Q rate we would obtain also using this framework are extremely tight. And I think if you have attended Lar's talk on Thursday, you have seen practical proof that it overcomes EUR in, for example, in decoy state protocols. And also, obviously, it recovers the tensor product model as a special case, so it encompasses all those previous developments as well. All right. Now, let's see what does meat has to offer for variable length protocols. So far we were analyzing the fixed length protocols, where essentially are the ones, as Florian mentioned, that makes an acceptable decisions and output a finite key of output a key of the fixed length. Whereas in the variable length protocols, it allows the user to adjust the length of the key based on the observed statistics during the protocol. So it's actually more practical to analyze these kind of protocols. So for that, we are going to first introduce a new family of entropies called F-weighted entropies, which are being defined for classical quantum states by the following expressions, where this F here is going to be called score function or trade-off functions, or sometimes called estimators. But to gain a little bit of an intuition of what this F-weighted entropy is, if we set F to 0, we would recover the usual Renyi conditional entropy. So if you look at the term within the log, you can see that these Fs are somewhat weighting this sum appearing in the log. So hence the name F-weighted entropies. So these entropies were first introduced by Van Hembeck and Brown based on a concept of quantum estimation factors. And the idea behind it was to develop a framework such that conditioned on each value of C, these score functions, lower bounds the entropic term, appear in the exponent. It turns out that having this framework such that these score functions bounds the entropic term is always really difficult. So we couldn't come up with that, but hopefully, luckily, we managed to make it work in some sort of average sense. In other words, it can be shown that non-negativity of these F-weighted entropies is equivalent to having these score functions lower bounds the entropic term in the exponent in a log mean exponential sense. So it is some form of average. But why do we care about these F-weighted entropies? So recall that for fixed length protocols, the length of the secure key was given by bounding this Renyi conditional entropy condition on the acceptance of the protocol. And when Hembeck and Brown showed that bounds on these F-weighted entropies actually giving us the key length on variable length protocols. And so the goal here would again be to finding bounds on the F-weighted entropies of the global states. So it turns out that F-weighted entropies also satisfy a meet statement, which we're going to explain very briefly. So if we look at the general form of the meet, as I explained earlier, the sequential structure, let us define the full estimator, F full, as the sum of individual estimators for each individual rounds. In which case, the global F-weighted entropies can be bounded by the sum of individual F-weighted entropies, except that we have to take the worst case over the output of these channels with the fixed marginal so that we can apply it to prepare measure protocols. So the way that we can think of this inequality is that basically this inequality tells us that we can accumulate single round estimators, these FCJs, into the full estimators to estimate the final entropy. So this idea of bounding these F-weighted entropies have been explored in various frameworks, the original EAT model, the generalized EAT model, and very recently the identical tensor product model and non-identical tensor product model. And we actually generalized it to the case where we have this sequential form while preserving the marginal constraint. Okay, so that means using this F-weighted meet, we can have bounds on the key length for variable length protocols. And in fact, the framework is actually even stronger than that. It allows us to choose different estimators in each round based on the history of announcements, which is something specific for meet if you want to use it for prepare and measure protocols. And this degree of freedom actually allows us to analyze fully adaptive protocols, which makes it mostly suitable for analyzing, for example, satellite QKD. And there's also something that I didn't actually mention, and that is that these framework that we developed these score functions F are somewhat a degree of freedom in the framework, meaning that choosing different F gives us different values of the key rate. And so a natural question is, what is the best value of the key, this F that one can choose to give us the highest value of the key rate? For that, I'd point you out to see the paper. We do have methods to find the good choice of these estimators such that it gives you the highest value of the key rate for your protocol that is compatible with the framework. All right, now to summarize, we provide a security proof for prepare and measure protocols without repetition rate restrictions via meet. The framework allows on-the-fly announcement, which is useful in practical scenarios. It leads very tight key rates. It is compatible with variable length protocols and can handle fully adaptive protocols, which is useful for satellite QKD. And as for the feature direction, well, obviously, we should apply it to more practical protocols and see what exact key rate we would obtain. And another interesting theoretical problem here would be to incorporate memory-based imperfections. So if you have attended Lars' talk, you might have heard that the meet framework already incorporate imperfections that are memoryless, but to have, for example, to be able to analyze source correlation problem within this framework, we need to somehow generalize the framework a little bit so that it can handle some form of the memory. And last but not least, well, can we go beyond meat, getting some form of a memory, secret memory, similar to what was existed in the JIT framework? Yeah, and with that, I'd like to thank you for your attention, and I'm happy to answer your questions.
Thank you very much, Amir, for the great talk. We have time for some questions.
Thank you very much for the very interesting talk. Yeah, as you said, the problem of source correlations is important in practice because in practice, the states emitted by Alice will, in general, have correlations due to memory effects in the modulators. I would like to know if you could elaborate a bit more into how difficult you think it would be to extend this to such realistic cases, or what are the hurdles that need to be overcome to achieve that?
That's a really good question. So basically, from the theoretical point of view, to be able to analyze these form of imperfections, we need to have some form of memory register that is secret, so that it doesn't leak information to the adversary. And this has already been taken care of in the, for example, in the JIT framework. But well, using the JIT, you have to live with this repetition rate restriction, which is not so much practical. But to incorporate that into this new framework, it means it leads some really difficult theoretical barriers to incorporate this extra memory register such that it doesn't leak information to the adversary, so that you can somehow store these imperfections within that memory register. Okay, and so I do believe it is possible, but it requires like major analysis.
But if I understand correctly, what would change if you have source correlations is that in the source replaced protocol, Alice's marginal state would not be in tensor product form, like her global state would be correlated. How could this be addressed using a memory register?
So, okay, so one way, so there are two ways to attack this problem. One would be to, well, as I said, going beyond meat, come up with the framework similar to the meat, but with having promise on the marginal not to be necessarily in a tensor product form, but some form of a correlation that we, to an extent, know how to handle, which is quite challenging because given that the way that the proof of the framework works is highly rely on the fact that you need to have like tensorized marginal for Alice's state. But another way to attack this is to somehow be able to subtract off the amount of correlations that are introduced by having this something other than the tensorized on Alice's side, and somehow subtract off some form of entropic quantity to incorporate this correlation into the framework. And so doing that, this latter version is actually possible if you would have some memory register to store these correlation into it and then pick it out of it at each round of the protocol. There's a really high-level picture, but yeah, I would say like if you want to actually look at the more practical, make it work for source correlation, we have to be able to generalize the entire proof such that the marginal actually doesn't necessarily have to be in a tensorized form.
Okay, that makes sense. Thank you.
Okay. Do we have more questions?
Hi. Yeah, thanks a lot for the talk. I'm just curious if you could summarize or like tell us a bit more about how difficult it would be to calculate the optimal key rate in practical setups. And maybe also you mentioned that you introduced methods for the optimal choice of this f function. If you could tell more about how difficult that is in practice also.
Okay, let me see if I have something here. So basically, if you want to evaluate fixed length key rate, all you need to evaluate is just this single round quantity. So this has already been taken care of. There are methods, for example, in Large's work is actually introducing one method to evaluate this quantity. So all you need is to have some solver to be able to evaluate this any conditional entropy. But if you're willing to somehow accept some looseness, you can use continuity arguments to convert this any conditional entropy to a von Neumann entropy by paying some continuity price. And then you use the existing solvers to evaluate the conditional entropy. But if you want to find the best choice of f, so unfortunately, I don't have any slides prepared for that, but roughly speaking, we showed that, I can find it right. Roughly speaking, we showed that there is some convex optimizations involving these f-weighted entropies and plus some inner product with f-weighted entropies and some distributions lies within the acceptance set. And so there's like a given convex optimizations that appears once you try to actually evaluate these things. And it turns out that optimization, if you evaluate the dual to that optimizations, the dual solution to that optimization gives you the optimal choice of these f's.
Thank you. Very clear explanation.
Yeah.
Right. Okay. I think it's time to move on to the next speaker. So thank you, Amir, again.
Thank you so much.